Hello and welcome back. So if you've ever run a Hello World container, you know how easy it is to get that one little thing up and running. But let's be honest, real-world applications, they're not that simple. They're usually a collection of different services. You know, a web app, a database, maybe a few others, all working together in harmony. Today, we're going to build one of those, piece by piece.
Right, so you've got this single container down. Awesome. But what happens when you need your web server to actually talk to a database? Now that is the real challenge we're tackling today. How to connect multiple, totally independent services to build a complete functioning application.
You know, for decades, we built what are called monoliths. Basically one giant tangled application where everything was connected to everything else. If you wanted to scale just one little part, you had to scale the whole thing. But Docker, well, it lets us build with these smaller, independent services, and that isolation is just so powerful. It means our database and our web app can live on the exact same machine without ever stepping on each other's toes.
Okay, first things first. Let's create the blueprint for our application. We're going to start with the stateless part. That's the web app that holds all the logic. And we'll create the recipe for its container. And that recipe? It's called a Docker file. Think of it as a simple text file that lists out all the commands needed to build our app's environment. From the base operating system all the way to our own code, the Docker file makes sure that every single build is identical and totally reproducible. Now, to really get a handle on build speed, you have to understand this key concept called layer caching. See, every single instruction in your Docker file creates a new layer. If an instruction hasn't changed since the last time you built it, Docker just reuses that layer from a cache. This can make your builds dramatically faster, but only if you structure your file in the right way. And here is the classic mistake. You copy all of your code first, and then you install all your dependencies. So what's the problem with that? Well, if you change a single line of code, even a comment, that copy layer gets thrown out and you are forced to reinstall all of your dependencies from scratch every single time. It is just painfully slow. Okay, but the optimized pattern is way smarter. First, we copy only the package.json file. That's just the list of our dependencies. Then we run the install. And only after that's done do we copy the rest of our application code. So now that slow npm install layer gets cached. It only reruns when our dependencies actually change, not every single time we edit a file. This is an absolute game changer for your development speed. So, our app is all containerized, but it's pretty useless without any data. It's time to add our second piece of the puzzle, the database. And with it, we've got to tackle the most critical problem it faces, persistence, or, how to actually remember things. All right, this is a crucial point, so listen up. Containers are ephemeral. By default, they're basically like an Etch-a-Sketch. The moment you stop and remove a container, everything inside it, all the files, all the data, is completely wiped clean. For a web app, that's usually fine, but for a database, that's a catastrophe.
Let that sink in for a second. Without the right strategy, any data you write inside the container is irretrievably lost. All your user accounts, your to-do items, poof, gone forever. This is the problem we absolutely have to solve.
And the solution is something called a Docker volume. The best way to think of it is like a dedicated external hard drive that you just plug into your container. This volume is managed by Docker, but it lives on your host machine totally separate from the container itself. So if the container gets deleted, the volume and all your precious data remains perfectly safe. Now, while there are a few different ways to save data, the best practice for production data, hands down, is using named volumes. They're portable, they're high performance, and they're managed by Docker, which makes them the go-to choice for databases. We'll save the other option, bind mounts, for our development workflow later on. Okay, we've got our two components, a stateless web app and a stateful database with a persistent volume. Now, we need to get them to actually talk to each other. The modern way to do this is with a user-defined network. It's kind of like creating a private little phone system just for your containers. Once they're connected, they get their own built-in DNS. What that really means is your application can find the database just by using its container name as a hostname. That's it. No more worrying about IP addresses that are going to change every time you restart. Now, you might see some older tutorials out there that mention a -link flag. Just ignore it. Seriously, that is a fragile, old system that's been deprecated for a long time. User-defined networks are the automatic, reliable, and officially recommended best practice for all container communication. Full stop. All right, this is the moment we've been building towards. We've defined our app, we've defined our database, and we've defined the network that connects them. It is time to put all of these pieces together and launch our complete application.
The sequence here is both logical and really important. First, we create the network. That's the communication backbone. Then, we start the database, which our app depends on. Next, we build our app's image from that Docker file we made. And finally, we run the app container, connecting it to both the network and the database. In that final command, there are two flags that are absolutely crucial. The .publish flag, or .p, maps the container's port to our own machine, which lets us actually see the app in a browser. And the .envel flag, or .e, passes in an environment variable that tells our app how to find the database, in this case by using the hostname todo_mysql.
Look, getting the application to run is a huge step, but making it robust and secure, that's the real goal. So let's cover the single most common failure you're going to see, and then a few essential best practices.
This is it. Without a doubt, this is the #1 question developers ask when they start with multi-container apps. You follow all the steps, everything looks right, but your application immediately crashes with a connection refused error. So why?
Well, the cause is a classic race condition. Your application container starts up almost instantly, right? But the database container, it needs time, sometimes 10, 20, even 30 seconds, to get itself ready and start listening for connections. Your app tries to connect before the database is ready, and bam, connection refused. The solution? It usually involves adding some retry logic to your app or using a little helper script to just wait. And finally, let's wrap up with 3 pro tips to make your application truly production ready. First, for security, always run your containers as a non-root user. Second, for stability, always set resource limits so one container can't crash the entire host. And third, for reproducibility, always pin your base image versions in your Docker file to make sure your builds are consistent today and a year from now.
So there you have it, a running, persistent, multi-container application. You've solved persistence, you've conquered networking, and you know how to fix the most common startup issues. But really, this is just the beginning. The next step is orchestration, scaling, advanced security. So, your application is running, but is it truly ready for the real world? We'll dig into that next time.